Investigation of Curves, Section 1, Equations and Properties of Curves. Video 4, Families of Curves, Polar Equations. In the previous two videos, we've looked at families of Cartesian and parametric curves. This time we're going to look at a family of curves that have been expressed using polar coordinates. Once again, we're going to look for features that are common to all of the curves or that are specific to just some of the cases. So here's an example of a family of curves using polar coordinates. Plot the curves with equations r equals cos theta plus k for the cases k is 0.5, k is 1 and k is 2. Let's have a look at this in GeoGebra. Now the first thing that I might want to do is to switch my axes. So I'm right clicking to get the graphics menu, and then where it says grid I can choose, instead of having X and Y grid lines, I can have polar grid lines like this. So it might help me to be able to sketch my curves a little bit better when I can see the polar axes like that. Okay, so the coordinates that we were given were r equals cos theta plus k. So I can just type that straight into the input bar. R equals cos theta. I can do Alt and T for a shortcut for theta, or I can just select it using this little pop-up menu on the right of the input bar. I could have selected my theta from there if you prefer. And then plus k, and when I hit enter, it asks me if I want to create a slider for k. And there we are. I can vary, there's k equals 1, and I can vary k to different values and see what stays the same and what changes about the curve. Now it asked me specifically about the cases k equals 0.5, k equals 1 and k equals 2. So let's have a look at those. K equals 0.5 first of all. Okay, so I can see it's got this loop just here, and then it goes round, it goes up, cuts the axis at 1.5 just there. And then if I go up and look at k equals 1, it's quite similar, but instead of a loop I've got a cusp just here, and it goes up to x equals 2 just there. And then finally for k equals 2, you can see it's sort of flattened off rather than having that pointy cusp that we had before. We've just got sort of like this flattening here, and then it goes around and it goes up to x equals 3 just there. So let's have a go at getting those down onto our paper. So here are my three sketches. First of all, the case k equals 0.5. So to draw this sketch, first of all, I noticed that I needed this loop here that went round to r equals 0.5 just there. And then once I'd done that, I noted some points that it went through. So it's going through this radial line here at r equals 1, and it's going round to 1.5 as its maximum distance from the origin there. And then I just tried to sketch it round, getting it as symmetrical as possible. For k equals 1, I wanted to make sure that I'd drawn this cusp that we're getting here at the origin. And again, I just noted down from GeoGebra some of the key points that it was going through in order to try and get my shape looking as close to the shape on my screen as I could. And then finally, for the case k equals 2, again, I've got the points where it's crossing the axes, and I've tried to make it mirror as closely as possible what I could see on my screen, and again, getting the general shape of the curve like this. So those are those graphs drawn out neatly for you. This is the sort of commentary that you would put with your sketches then. So first of all, we've got a line of symmetry . And that would be in the x-axis or the polar axis if you want to express it using polar coordinates. We've also got a loop and that's in the k equals 0.5, and we've got a cusp, and that was when k equals 1. And we might also want to talk about boundedness. So all of them are bounded, and we can express our boundedness using our polar coordinates here, that r is less than or equal to k plus 1 for all of them. So when it was 0.5, r was always within a circle of radius 1.5. When k was 1, r was always within a circle of radius 2. And when k was 2, it's always lying within this circle of radius 3. In this video, you've learnt how to investigate a family of curves expressed in polar form and how to identify relevant features of the curves.